Okay. Let me check if this is convection. Plus, sorry. New share. Okay, so we are on the first part of convection. There are two parts in this. Forced convection, that is. And as a review, last meeting, we have discussed the formula that we will be using in determining the heat transfer rate via convection associated with flowing mediums such as liquids and gases. And we have discussed as well the different dimensionless numbers. And let me just minimize this one. So the dimensionless numbers, Prandtl number, and then we have Nusselt number, and we have the very important Reynolds number, and the not so common Gretz number, Fourier number, and the Peclet number. So all of which are semi-empirical in nature. We have also discussed the formula to use when flow is laminar. And we also discussed the formula that we will use when flow is turbulent. But generally, class, our H, the very important heat transfer coefficient, is higher in the turbulent region or turbulent flow regime. Okay, so we will discuss now the sample problem, which I have, I think, read last meeting. And we will write down the different information that we could for this particular problem. So you're given here air at 206.8 kilopascal and an average of 477.6 Kelvin, which is being heated as it flows through a tube of 25.4 mm inside diameter at a velocity of 7.62 meters per second. Now, the heating medium here, which is steam, is at 488.7 Kelvin. Now, it's condensing on the outside of the tube. So since the heat transfer coefficient of the condensing steam is several thousands of watt per square meter Kelvin, and the resistance of the metal wall is very small, it will be assumed that whatever is the temperature of the air, which is comparable to that of the steam in the outer side of the wall, will be the same surface wall temperature. Now, for this problem, you are asked to calculate the heat transfer coefficient for a length to diameter ratio greater than 60, and also the heat transfer flux, which is your heat transfer rate divided by the area. So that I will not anymore go to Jamboard, so I will just have here another sheet for us to use for the solution of this problem. Okay, so our problem goes this way, that you're given air at the given pressure and temperature, which is heated as it flows through a tube. So air is in the inner part of the tube and it's being heated by steam. So if you're going to write down the given information, this is our pipe. So we have air inside the pipe. Now here outside is steam. And we assume that air is flowing continuously in this particular pipe. Okay, we'll get the information that we have on the problem. So your air is at 206.8 kilopascal and 477.6 Kelvin. So let me just get it from here. That way we won't have to keep on erasing what's written already in the previous slide. So your air for this one, in the inner part of the tube, this is at a pressure of 206.8 kPa. And the temperature, the average temperature is 477.6 Kelvin. That's for the air inside the pipe. And then the inner diameter of the tube, so I will have ID here. It's 25.4 mm. The velocity of air, so I will just indicate it in here, is 7.62 meters per second. Now, heating medium is steam. So your steam temperature, I would like to have here A for air, and your steam temperature is 488.7 Kelvin. Now, it's to be assumed that the wall temperature is more or less equal to the heating medium temperature, which is the steam, due to the heat transfer coefficient of your steam, which is several of thousands already compared to the conductivity of the pipe wall. Another thing that is asked here is, okay, how many? So 1, 2, 3, 4, 5, 5. So 5 given information. 1, 2, 3, 4, 5. So that's 5. And we are required to determine the following. So for letter A, you are required to determine the heat transfer coefficient. So that would be the H for an L to diameter ratio greater than 60. And for letter B, you are asked for the heat flux. So that would be the ratio of the Q to the A. So this is our given information here. You might as well, we'll have another slide, but this will still be appearing unless I write everything, clear everything. So please take a screenshot already so we won't have to go back already to the previous slide. So I will just have to clear this anyhow. I need to clear this. Any questions so far as to the given and the required information? So we have air to be heated by steam. These are the things given about the air. This is the inside diameter of the tube where your air is flowing to. This is its velocity. And we have the temperature of the heating medium. And we assume that the wall temperature of the pipe is the same as that of the heating medium, which is that of steam. Okay, so if this is our given, we need to work our way through the given. Let me first clear the drawings if there are no more questions here. No more questions here? Okay, I think there's none. So I will clear now this one. So we will go to the solution to the problem. So what's the solution to this particular problem? The first thing that you're going to do is you need the actually, if you're not going to follow the way it's given in the book on how the particular problem is to be solved, you're going to start with the formula that will lead you to the required information. So the required information is the H, the heat transfer coefficient, and we need as well to get the ratio of the Q to A, or that's the heat flux. Now, before we can even determine the heat transfer rate, there's a need for us to establish the flow. And if we need to establish the flow, what parameter is it that we need to know? If we need to establish what type of flow we have, we need to know first you cannot solve for heat transfer rate, you cannot solve for heat flux unless you first establish this one. And what is it that you need to establish? Anyone? Based on our discussion yesterday, before you before you can determine what the problem requires, especially if convective heat transfer is the principle that is to be applied, what it is that you need to establish first. You need to establish the what? Anybody? You need to establish the flow, whether it's laminar or turbulent. So if you need to establish the flow, whether it's laminar or turbulent, what particular dimensionless number will you be utilizing to establish the flow? Okay. What is that particular number? Dimensionless
Reynolds
number.
number, miss.
Okay, that would be the Reynolds number. So class, please participate when I ask a question. If you know, I need to know as well that you can follow through. Okay, so if it's the Reynolds number, the formula for the Reynolds number as discussed yesterday, and I think this is not something that is new to everybody. What's the formula for the Reynolds number?
Rho dV over mu, miss.
So that would be rho dV over mu, or dV rho over mu. So I can establish the flow if I have all the parameters that I need for the Reynolds number. So the first parameter, we need to check what we know, and of course we need to look for what is not given. So as for the diameter, do we know this already, the diameter? Okay, the diameter is given. It's given a while ago as 25.4 mm. So velocity is also given. So that leaves us with the density and the mu. Okay, so let's say I'd like to first determine the density. Okay, what will be the formula that I will be using? I will just label this as equation 1 for now, because I need to go back to that equation once I have everything complete. So if it's the density that I'd like to determine, so any suggestion on how am I supposed to determine the density?
Mass over volume, miss.
Okay, density, actually, I did not specify my question. If it's just when we talk about liquids, it's mass over volume. But the flow that we're considering here is the flow of the heating medium. Okay, because it's the heating medium actually that is the, shall I say, our heat transfer coefficient, which we will be needing in our heat transfer rate, is dependent on the flow regime in which the heating medium is could be classified under of. So it could be laminar, it could be turbulent, or somewhere in transition between laminar and turbulent. So having said that, tsakto man siya ang hambang nga density is mass over volume. But in our case, the problem is saying that our heating medium is the what? In this case, our heating medium is the steam, right? And the thing that is to be heated is air. So we need to determine, so both the heating medium and the medium that is to be heated are all in the form of gases. So ang formula nga ginhatag ni Vincent, was it Vincent? Mass over volume will only work for liquids. So if I need to determine the density of the fluid that is to be heated, and that is the air inside the pipe, what should be the appropriate formula to use? Mass over volume is for liquids. In the case of gases, kiti wala gid kita dili liquid sa problem ta. Ang medium nga initon kag ang medium nga mainit sa iya are both gaseous in form. So if we want to establish the flow of the, let's say for example, in this case, we would like to establish the flow of the air inside the pipe, what should be the formula that I'm going to use? From Chem 1. What did you learn in Chem 1 regarding density of gases? Is there a need for you to assume something? Dexler, do you have any idea on how are we supposed to solve for the density here? We're dealing with gases.
Density of what?
Density of air. Even if it's density of steam, we can use the property in the steam tables for that. Okay. But if it's the density of air, what is it that we're going to use? The formula that we're going to use.
Ang iya ka ideal gas law, mates.
Okay. Thank you for that. So very good. So you need to assume ideal behavior. And if you assume ideal behavior, we go back to the ideal gas law equation, the PV and RT. And from the N here, you can write mass over molecular weight. And you still have RT here. We will derive the formula for the density of a gas from the assumption that our gas, in the case of air, is behaving ideally. So we transfer the volume in here, we transfer the molecular weight in here. So you have P times the molecular weight. RT, I will transfer here, should be equal to the M over V. The M over V that I think Vincent mentioned a while ago, was it Vincent, is of course the density. But in this case, class, your density for air will be based on the pressure, the molecular weight of air, the universal gas constant, and the absolute temperature. So as to what universal gas constant you will use, it depends on the formula that you are, or rather the units, not the formula. It depends on the units that you are using. So now going back to what I have written here. So since we know already density is the product of the pressure and the molecular weight divided by the product of RT. Okay. This would be now equal to, so I'll place here. So the pressure that is given in the problem for air is 206.8 kilopascal, or we can convert this right away to 1 kilopascal equal to 1000 pascal. Okay, then we have the, what's the molecular weight of air? Thermodynamics, what's the molecular weight of air? Okay, let me see. 29. So to be exact, Bia, thank you for that. The molecular weight of air is 28.97. Okay, kilogram per kilomole, or gram per mole. Okay, so that's the molecular weight. And let me say, cancel this one. And then we have for the R, what's the appropriate R to use here? Since we're using SI units, what R are we to use? We'll be using the 8.314, right? Joule per mole Kelvin. Okay, now since this is per mole and this is in kilomole, I need to convert. So I have 1000 mole per 1 kilomole. So I will cancel this 1000 here, and this kilomole will cancel with this kilomole, and this mole with this mole here. Then I need a temperature. So the problem gave us a temperature of 477.6 Kelvin for the temperature of the air. So we will now cancel the Kelvin temperature here. So we have the joule unit here. The joule is, by the way, Newton meter and we have the Pascal in here, and we have the kilogram. The corresponding unit for density, if we have all this in SI, will be in kilogram per cubic meter, which I will leave to you as an exercise. Anyway, if all the units are agreeing, then you won't have any problem coming up with the appropriate unit for density in SI. So you have 206.8. You multiply that by 28.97. We divide by 8.314. And we divide again by 477.6. That should give us a density of 1.509 kilogram per cubic meter. So this would be our density now that we need to substitute in our Reynolds number. So please take note of that, because we will substitute it in here later. So any question for now? We have already the density, so we can substitute to one density and viscosity. So is viscosity already known? Do we know already viscosity? So the problem does not give us for now the viscosity. So since it's not given yet, you need to determine the viscosity. As to the viscosity of air, it should be based on the temperature of the air, the average temperature of the air, which is 477.6. Now, where are you going to get this? So I will erase everything here. And you need to go to a particular appendix, or you need to go to your Paris Chemical Engineer's Handbook, section 2 for the viscosity, viscosity of air. So let me show to you a cut of the appendix as found in John Copley's, where you can read the properties of air. So for the one for the air that we're now given in the problem, we need to base it on its temperature. So the temperature is this one, 477.6. And for now, we need the viscosity, which is 2.6. So you now have the viscosity and the rest of the information. Then you can go back to the problem and substitute the values to the Reynolds number formula. So for now, I'll be getting this value here. And since you see in the table that it's times 10 raised to 5 class, when you substitute it, it should be now 2.6 times 10 raised to negative 5. Because the values that you could see in this column are already multiplied to 10 raised to 5. Okay, now so I'll erase everything here, everything here, and go back to our empty sheet. So as a continuation now, if we substitute to the Reynolds number, so our inner diameter is an mm. So if we want to have everything in SI, we need to convert it to meters. So converting it to meters would make it 0.0254. Because it's 25.4 mm. So 0.0254 meters. And then this is for the D. For the velocity, the problem gave us that the velocity is 7.62. And for the density, we just got it a while ago, 1.509. And we divide it by the viscosity that we just read, this one. In the next slide, I will show it again later, which is 2.60 times 10 raised to negative 5. Now, this will give us a Reynolds number equivalent to 1.122 times 10 raised to 4. Or let me check, because I'm using a different value for the density. So you have 0.0254. We multiply by 7.62 by 1.509, and we divide by 2.6 raised to negative 5. So Make 3, 2, 1, 2. This is 3 already. Okay, so 1.123 times 10 raised to 4. So this would be like, what flow is this now falling into? You multiply it by 10,000. So that would be now giving us,
Turbulent.
so our flow is turbulent. Okay, so since it's turbulent, the formula that we will be using is that for cider and teak. Wait, let me check on top. If it's turbulent flow, I think cider and teak is for laminar. Okay, just to refresh you, I will not erase that. This one is for greater than 6,000. So it's not cider and teak because cider and teak is for laminar. So the one that we'll be using is the one for turbulent, which I have shown in here. So anyway, I will go back to that sheet where we are writing, and that formula, which you cannot see properly because of my handwriting, would be this. So you have the Nusselt number, which will lead you to the very important heat transfer coefficient, which is H. And it's to be solved using this 0.027. The Reynolds number, which we just solved, should be raised to 0.8. And it should be multiplied to the Prandtl number, which is 1/3. That's right here, 0.33. And the ratio of the viscosity, the bulk density, viscosity, and the wall viscosity. This would be 0.14. So just like what we did with Reynolds number, we need to check in here what we know and what we still need to find. So we have determined already the Reynolds number. The Prandtl number class can be read from a particular table. Okay, the viscosity was already read a while ago, which is 2.6. That's the bulk viscosity of the air flowing inside the pipe. The thing that we need to find is the viscosity at the wall based on the wall temperature. And that would be taken later. I'll show to you the table. So as for the Prandtl number, I will also give it to you in a little while. So it will also be taken from a particular table for for air, because air is the one that is flowing inside the pipe. This one we know already, and this one we also need to get from a particular table, the conductivity, the thermal conductivity, that is. So what we need to find right now, I place here a question mark. You need this, you need this one, and you need this. That way, the only remaining unknown here is the heat transfer coefficient, which we will be needing for the heat flux. And of course, for the first unknown, which is itself, the heat transfer coefficient. So I need to find the K, we need to find the Prandtl number, and we need to find the viscosity based on the wall temperature. Any question for now? Okay, so please take a screenshot of the formula because we need to go back to that later, and you can follow through because I need to erase. Now, where do we get we get the Prandtl number and the viscosity based on the wall temperature? Actually, they will be all read out from one particular table if you're using a table found in the appendix of Gen Kuplis. But if not, if you're using your Paris Chemical Engineer's Handbook, I suggest you try to use it now. That way you will be familiar where you're going to get the values. Then it would be in section 2 as well. Okay, so I will erase now. And this is the table that I'm referring to. So in the table, for this particular temperature class, again, we already got the U sub B, the bulk viscosity, and we need to read simply the Prandtl number here. That's the Prandtl number. And there's another viscosity that you're going to take from this table based on the wall temperature. Now, The wall temperature class is based on the temperature of the steam, and that's the 488.7 Kelvin. And since it's not in here, the 488 is in between 477.6 and 505.4. You will need to interpolate. And so for us to save some time, I will just directly use the value that is indicated in the book as to the viscosity based on the wall temperature. So that particular viscosity is 2.64 times 10 raised to -5. Actually, class, these properties are not linear, but we just approximate because we don't have graphs to read it from. So, kalaban, non-physical properties are not linear. So, they are actually curved somehow. So, but we don't have those. So, we just approximate. So, it's 488 in between these two values. So, it's expected that the value that you will be getting for your mu sub W is also in between 2.6 and 2.71. So this is the value that we're going to use, that we're going to use for the mu sub W in the formula. So we have it already. The other thing that we need to get is the K, which is the thermal conductivity constant. So where are you going to get the thermal conductivity constant? In the case of, let me check. So we have it here. Everything is in here. Okay, wait class. The problem did not give us the K. Let me show to you the problem so you can help me find the K. It will just clear the drawings here. And we'll go back to the problem that we are reading. Wait class, hindi siya mag-transfer. So you're given the properties of air, the inside diameter, and you have the velocity. You have the temperature of the steam, the heat transfer coefficient. Okay, so there was no mention of the thermal conductivity constant here. So it's just a wonder why, where did the K, which is 0.03894, came from? So let me just write here the formula that we need to substitute everything. So we'll have N and U. So HL, D over K. And you have 0.027. I will substitute the Reynolds number already. The one that we got is 1.123 times 10 raised to 4. And we're going to raise this to 0.8. The Prandtl number that I have shown to you where to get is 0.686. Raise this to 0.33. The viscosity, the bulk viscosity is 0.0260, and that at the wall is 0.0264. The ratio of these two we need to raise to 14. Now, if this value we will equate to HL, I will place HL here, and then the diameter in meters, which is 0.0254. And the thermal conductivity constant class is assumed to be, though it's not stated in the problem, to be 0.03894. And the material in which our,
Excuse me, miss. Sa
yes,
appendix, yagin kwa, miss.
dali lang. Ano yung basihan niya?
Ang 477.
Ang iyas ang steam? ang temperature sang air.
Oh, there again, base.
Wait lang ha. It's supposed to be the property of the pipe itself, of the tube itself. But in this case, it's not provided by the problem. So, and it was assumed, class, in the problem that the resistance of the metal wall is very small. So that is why it's not using the thermal conductivity constant of the wall itself. It should be that of the tube wall I'm referring to. But since it's assumed already in the statement here that it's very small, so the thermal conductivity constant that was used is that of air. So you have to understand why nga ang gingamit niya is that of air. That would be point, isulat ko lang anay ha, 0.0894. And all the values that we have here, the corresponding values that we have here on top. It's only in the case of this problem, class, that you are using the thermal conductivity of the fluid that is being heated. Let me emphasize that, because it is the problem also that mentioned that the thermal resistance of the tube or the wall itself is very small. So it will not offer any resistance to heat transfer. So you're going to, as what Jericho is saying, that was Jericho, the problem used the thermal conductivity of the air itself that is flowing inside the tube. So from in here, you'll be getting the HL value, which is, I'm just going to use the value that is given here in the book, which is 63.2 watt per meter squared Kelvin. So I hope you have that in mind. When we speak of thermal conductivity, actually it's that of the solids. But in here, as again, as the third time I mentioned, it's very small. So that is why we're using that of the air flowing inside the tube. So this is our HL, 63.2 watt per square meter Kelvin. Let me clear this one so I can point out to you the table where you get the K as well as what Jericho has pointed out. Okay, so same temperature. And you're going to get the thermal conductivity constant here, which is 0.03894. Okay. If the problem is not saying that your wall or your pipe resistance is to be negligible, the K that you're going to use is that of your pipe or your tube. Because in the first place, your thermal conductivity is associated with the solid where heat is to be transferred through. Okay, so in this case, it's read from this particular table, 0.03894. Same table where we took our mu, our Prandtl number. Yes, our mu and our Prandtl number. Okay, that for air. So now we have already HL. We can solve for the, okay, all the markings. So go back here. We can go to the heat flux. So for letter A, class, that's already your answer. The heat transfer coefficient. And that's 63.2 watt per square meter Kelvin. For letter B, it's actually Q over A. So in that case, you need a formula. That's equation, the primary equation that we're using for convective heat transfer. I will just write it first here. The primary formula, class, doesn't look like this. The fundamental formula for convective heat transfer has the A written here. And since letter B is asking for the heat flux, we just transfer the A here below the Q, and that will give you the remaining variables here to multiply. So you use the value that you got in A for the heat transfer coefficient, and then you use the wall temperature, which is 488.7, and then you use the This one is the temperature of the fluid, the bulk temperature of the fluid, which is 477.6. So now you have the heat flux value, which is 701.1 watt per square meter. So this is your heat flux coming from the fundamental formula of convective heat transfer, which is actually Q equal to HA, written in this form, T sub, let's say for example, 1 minus T sub 2. Okay, that's the general formula. So we just transferred the A in here. Okay, what is important in this problem class is first you have to establish the flow and you know where to get the characteristics, the properties of the substances that you are going to substitute on the formula. You can find this particular problem in Jean Coupley's in 4.5-1. Any question here before I proceed? Okay, so I think there's none. So let me proceed with the next part here in our slide. So that's our first sample problem taken from Jean Coupley's. Now, for turbulent flow inside pipes, for air at 1 atmospheric pressure, turbulent flow already, we can already estimate more or less the HL, the heat transfer coefficient, using this particular formula, as long as it was already established that it is turbulent flow. So in that particular problem, actually class, pwede man ninyo gamiton ang ininga formula provided that you have the kinematic viscosity here. You have the V's here. Okay, that's in syntestone, this one. Now, as for water on the range of 4 to 105 degrees Celsius or 40 to 220 degrees Fahrenheit, this would be the convective heat transfer coefficient also. And for organic liquids, this would be your HL as an estimate of the value of the heat transfer coefficient. Now, you'll be able to find, by the way, class, the V that is italicized in here, this one, is not kinematic viscosity. It looks like kinematic viscosity, but these are actually, as defined in your textbook, as just simple velocity. So you may use this particular formula for air, as long as it's turbulent. For water, this is the temperature range, and this is for organic liquids. You'll be able to find this also in Jean Coupley's, the new edition, the Philippine edition, in page 262. Okay, a more direct way of determining the heat transfer coefficients for the substances that are indicated. Now, for heat transfer coefficients for flow inside helical coils, if we want to approximate the value of the heat transfer coefficient, then this would be the corresponding formula. Applicable only for Reynolds number greater than 10,000. And HL in this formula is the equivalent straight pipe of the tube. Since it's helical, it's something like this. So what would be the corresponding heat transfer coefficient if it were a straight tube? Okay, that is why you have this correction, class. So that way you will have this new H2 substitute in the formula for your heat transfer rate, in which you have the heat transfer coefficient. The D with the subscript coil is the diameter of your coil. So this one is for helical coils. I don't find it here in Jean Coupley's. Probably I got this from a different reference book. So please take note of this and check as well if it's found in McCabe or in your Paris Chemical Engineers Handbook. Now, we know already what formula to use if the flow is laminar or if the flow is turbulent. What if it's somewhere in between? So this particular graph that you are seeing here is also having an equivalent in Paris Chemical Engineer's Handbook. Sad to say, plus my Paris here is only 8th edition. I'll try to have the soft copy of the 9th edition and check where the equivalent of this particular graph could be found in your handbook now, because you're using the 9th edition. This one is applicable if the flow regime is the boundary of laminar and turbulent. So only used on this particular region. And in this graph, it is to be interpreted that you use this particular first graph if the L over D ratio is 235. The second one if it's 180. The third one is if it's 120. And the last one if it's 60. So you use the corresponding curve depending on the L to D ratio. And you need, of course, to find this one in here. And I think that will be illustrated in the next sample problem that I will be discussing tomorrow before your quiz. In here, you have the properties. I think all of these are all properties except the H that you are seeing here on the first rational expression, the H over CPG. Okay, so we'll be discussing the application of this in the next sample problem. Now, if we're talking about heat transfer coefficient for non-circular conduit, kung hindi siya circular, ang cross-section ng imo conduit, the equivalent diameter is equal to the inner diameter of the outer pipe minus the outer diameter of the inner pipe. So we are interested for the equivalent diameter of the annular space. If it's not a non-circular conduit. Now, we have a long sample problem after this tomorrow, so hopefully we can finish this in 1 hour and a half before we have your quiz by 3 to 4:30 tomorrow. Now, any questions so far now, class?
Yes.
Yes.
The only statement, Miss Amon quiz, September 1.
September 1. Later in your quiz?
Yes, Miss.
Dali lang din.
Are nasa kanwas.
Kaya ang inyo, galibwas meeting sa ako, nag-confuse ko kay may process control man ko nga Thursday, nga synchronous. Check, dali lang din. So we will have a 1 hour meeting. 1.5 hour meeting, then we'll have your quiz. Iya, gali sa process control was. Okay, September 1, 3 to 4:30. Sige. So we'll continue our discussion later, 1:30 to 3. Then we'll have your quiz after, because tomorrow I think it's asynchronous na. 1 hour lang, so hindi enough for your quiz. Thank you for reminding me it's today. Anyway, it's there anyway in Canvas. If I cannot meet you online, you can still get the quiz. Any question for now, class? I will stop sharing. Drexel is sending me a message. Wait, class. Drexel, is this 9th edition already that you're sharing to me?
Yes, ma'am.
Okay, thank you, thank you. So you have the 9th edition. Anyway, shared to everybody. Thank you for that. I think what I have is the 8th edition, the old one. But still, you are to check the graphs, the equations that I am sharing to you, because they are taken from our textbook. What you can really use is the one that you have in your, or the equivalent that you have in your handbook. So please double check always. And use the, if you don't have the hard copy of your handbook, use the appropriate edition. Actually, bala class, ang appropriate edition nga ginapagamit nila, iya gyapon sang 8th edition, hindi iya sang 9th edition. But since wala na print ang 8th edition and you have the 9th edition, then you better make sure that you know where to find in your edition the properties, the formulas, the tables, because it's really very important. Because that's the one that you're going to use. Okay, so I see you later. We'll just have lunch. I'll see you at 1:30 class. So I need to send you a new Zoom link for that because I forgot. I thought it's tomorrow. Okay, bye for now, class. I see you later, 1:30. Thank you.
Thank you, Miss.
Okay.